Hi everyone, I'm Qianwei from University of Michigan, and today I'm going to introduce my project in this program, which is efficient and robust neural predicate learning from demonstration. So before we go into details about this project, I want to start this introduction from a very simple problem that how can robot to make a burger? So, for example, if we have like initial state that there's a lot of different ingredients, like patty, cheese, bread, across the rooms, and we have a robot, we want the robot to make a burger for us. For to solve this task, we can have very simple rule that just like a bunch of pick and place. So pick the bread first and paste it, and then place the cheese and place the patty and the bread. And for that, we can like make the robot to have a burger for us. But so if now we want to like the robot to make different burgers like uh there's a lot of different types of burgers, and now we cannot just apply a simple rule for both of burgers. So because it will be very labor intensive and need a lot of hard work to accomplish this. So we want a like very simple abstraction to represent different types of burgers. For now, here we want to introduce the predicates. The predicate is like a symbolic abstraction for the world. For example, in this slide, we can use a simple predicate called on to represent different types of burgers here. So basically, all the burgers can be represented as like a bunch of on, like bread on cheese, cheese on patty, patty on cheese, or cheese on bread. So using the predicate, we can have some generalization to different settings and tasks. So now we have already have a very basic understanding for what is predicate. So now we want to introduce the related word for our project. So our project lies in the big domain of imitation learning, which is also called learning from demonstration. So in its existing works, there's one category which is called neural methods. There is some a very fancy method which calls like sufficient policy or pi zero, and their limitation is like they have the like, difficulty to generalize to tasks significantly different than those seen and training time. And although there is some neural symbolic method, they learn the predicate we have introduced from the demonstration and apply those predicate in planning and use because predicate have the generalization capability, so it can perform better than those purely neural method in some domains which like requires you to like to do long horizon planning. But in neural symbolic method, there's two ways like grammar and VOM. They use some predefined rules to generate the predicate from demonstration, and their limitation is like they have very restricted state space. For example, in grammar, it can only apply to those domains have high level object features such as shapes or size, and the VOM method can only apply to image domain. But also now there is a new method coming out. It's called bi-level learning, which can learn those neural predicates from demonstration directly, and it can apply to different state space like the point cloud, image, or some high level, some shape like shape and size. But the one like there, it has two major limitations, which is efficiency and sim to real gap. And in our work in this project, we are working on address these two limitations and makes a bi-level learning framework more robust um, and applicable in the real world. So this is the whole framework for our methodology. So let's start from the training time. So assume we have a bunch of demonstrations. Now, in most of the domain, we use 500 demonstrations, which are like bunch of action trajectories. So you have the state and the action, and state and action, like, and so on. So first, from the demonstration, we have a very incompleted PDDL, and then we let the LM to complete it for us, and then we can derive some predicates and use the neural classifier training to like complete these predicates. And then we proceed into like loop thing. We propose using LM to propose a symbolic effect and using the effect to generate the label for neural classifier, and using the loss for the classifier training to validate whether the effect is correct or wrong. And then we can get a bunch of predicates with these classifier and symbolic effects. And we use the loss to threshold them and get a large pool of predicates. And then we go into predicate selection and get the final set. Then we learn the operator and sampler from those predicates and demonstration data. And then when we go like proceed into inference, because we have already learned those predicates and their classifiers, so we can ground those predicates in our observation, and then we pass our goal into that, so we can use the fast downward to generate a symbolic plan for us. For example, we can like place on T-balls first, and then pick spoon and place aside spoon. That's what we call symbolic plan. And then each step in this plan is a high level action, and we execute this action and then we will get a new observation, and we can ground predicates again and replan again until we achieve all of our goals. And because one thing we're addressing here is efficiency, because we are using LM to make the predicate invention faster. So here's the result we got, that in each domain we are a lot faster than those the original bilevel learning, which use a tree search to search for the predicate. But and simultaneously we can maintain our accuracy in chain and test. And also one thing we are doing is like validate those bilevel learning framework, predicate learning framework in real world, and we are working on to set up the experiment and doing the real world evaluation. And thank you.